Yo, niaje, hapa ni nworksinc Radio Podcast episode 35 na niko na mgeni hapa atajiintroduce.
Afternoon, naitwa John Karaoke.
John Karaoke.
Yeah.
Wewe ni physicist.
Physicist. Na nataka tuendelee sana kusoma maneno za quantum. Na leo ningetaka tuangalie maneno ya field theories zenye quantum iko based on.
So, quantum field theory. Hiyo sasa ni nini exactly? What is quantum field theory?
Ni the dimensions that our system or our universe uses. Basically, we are used to a 2-dimension or a 3-dimension universe, but quantum came up with an extra dimension or more dimensions.
More dimensions. Kwa hivyo si venye tu tunaangalianga life venye iko ati direct na nini. Kuna vitu ziko ndani zina affect each and everything.
Yes.
Each and everything, yeah?
Yeah.
Aya, hebu tuingie tu direct kwa hii quantum field theory. Hebu niambie some examples ama ni gani hizo ama tuingie deeper into it tuone ni aje.
Let us look at our quantum field theory as a framework that will try to combine the classical mechanic with special relativity in the quantum mechanics itself.
So ni zote pamoja.
Putting
them all together.
To put together, and then we are going to distinguish one from the other fundamentally.
Okay.
Yeah.
Okay.
So there are theories that our physicists tried to relate our universe with
through experiment
and observations. Well, they started with predictions. Let's say they predicted, and now we are at the part of studying the prediction. Anyway.
Are we understanding because the examples the examples went through they predicted.
As they predicted. And our father of physics, like Albert Einstein, may have differed with some theories.
Yes.
And some theories before maybe he died, he could have accepted them.
Yes.
Which currently we are working upon them.
Okay.
Yeah.
Okay. Let's start with one. What's string theory? String theory in Albert Einstein, no?
No, string theory was for Gabriele Veneziano. And
what was it about?
It was an accidental observation or experiment. So Gabriele was trying to look for an amplitude from something, like a string. And the amplitude is the height of the wave. Now let us give an example of a string of a guitar. When it is plucked, it vibrates in a different, and the amplitudes from the top to the bottom of those strings are very different. So now, the part of now the Veneziano was trying to look at is the smallest part, is what now the microscopic, the atomic that causes that vibration.
Okay.
So he decided to use an example of a string. Yeah.
Okay.
Yes. So when you sweep a string like this, it is like you are spinning something.
Yes.
It can either be an electron of 1 spin, 0 spin, half spin, 3/2 spins, or different spins.
Okay.
So he was trying to look at the smallest, the microscopic part of it, the electron part of it. How is this electron vibrating?
Electron,
electron, the smallest.
Kwa atoms, kuna electron.
Yes. So the string theory itself is one of the most interesting parts of our quantum mechanics, and it's a part that I would like our listeners to ensure they understand before we leave this session.
It's quite interesting, right?
Yeah. Because string theory really tries to unify all the 4 forces. We have 4 forces. In
gravity.
We have gravity, yes. The second force we have our
electromagnetic
force.
Iko kila mahali.
The third one, we have a strong nuclear force. And the fourth one, we have a weak nuclear force.
Hizo weak na...
A strong nuclear force tries to to bring our nucleus together.
Oh, they're pulling them together.
Yeah. A weak nuclear force tries to keep away our electrons don't come together.
Oh, they're losing electrons.
Yeah. Instead of coming together, they part away. Yeah.
Okay.
Now the string theory tries to unify all those forces. Because, for example, let us say something like gravity. Whenever we swipe our string like this, it may be going in a negative direction or in a positive direction.
Clockwise or counterclockwise, right? Yeah.
So, but that is our electron. That is how you have another force now we are calling electromagnetic force. The electromagnetic force is the force now in our electrons.
Oh,
yeah.
Okay.
So, the string theory tries to
unite all of them.
All those fundamental forces.
Okay.
Yeah.
Because, I read to talk about it, and they were saying like in the atom, the nucleus is in the middle.
Yes.
And the atom, the electron are around. And they move on a certain path.
Yes.
Like a certain path, like a circle. For example, it's not, is it like a circle?
It's a field.
A field,
We are talking about quantum field.
Yes.
It's a field now.
So what I read is that these electrons, they move from one level to the other without anything in between.
Yes.
So that is part of string theory.
That's part of the string theory.
Okay.
The threads of the string now moving up and down.
Yes. Without any effect from between the fields.
Between the fields.
Okay.
Yeah.
Okay.
And now, a common word here is unifying factor. Because let's say our electron was on a field that is flat. And whenever we are on Earth, we say that we have gravity.
Yes.
Let's say gravity is something imagined. So, electron, that's a small part, that's a small thing. When we think of gravity, if you drop that electron on a surface, we expect that surface to go down.
Down, yes.
Yeah. No, for example, in our string, we expect our string to go on the negative side of the
down.
Yeah. The string bars there.
Okay.
Yes.
Okay.
Yeah.
So that is part of the string theory, which means it is the fundamental theory of the universe. Can you say that?
Yes.
Because if it touches gravity, electromagnetism, strong force and weak force, that means it caters for heavy.
Yes.
Even the planets, how they already have their own path that they go through.
That they go through the ellipse. We call it an ellipse. Yeah. And the ellipse. Now, that's why the Gabriele Veneziano tried to work for the little particles, but he used a string because these particles, they must have a certain connection wherever they are.
Yes.
But that connection is something that is very hard to observe, and it is so microscopic.
Yes.
It is like
it has not been seen in short.
So he tried to use an example of a string. Yeah. So it's not basically a string.
Yeah. It is just like theoretical. Because I remember these are theoretical.
So theoretically, Veneziano was trying to bring us to the basic part of the particle, the neutrons, the protons, and the electrons. Yeah.
So that is why every metal has its own fields, electromagnetic fields.
Yes.
Electrons, neuron and protons.
Yes.
So that is basically what the string theory is about.
The string theory is about those small particles themselves. How do they behave in their world?
It is also small and also big because when you look at the universe, everything rotates in its certain path. All of them.
Yes. And that part, I would like our listeners to know that, for example, because in this topic of quantum, one thing we use a lot is light.
Yes.
For example, light in that world of microscopic objects, we assume that light passes through those particles like a string. Yeah. The barriers that we say light from the sun takes some minutes, vacuum. Yeah. We take it like a wave. It comes like a wave. Now that is our string. Our light is an electromagnetic wave. So light passes those electrons. Now the ones that we are saying are
as a wave.
As a wave. Yeah.
Oh, okay.
Yeah. So our listeners should like
try and understand a wave.
a wave. Yeah.
Like maji venye ripples of water when you
vibrate
kigonga inatoa vibration moja.
Yeah. So hizo vibration huko katikati kuna tu vitu vingine tuna exist hapo. Utondi tu sasa tu protons to electrons to neutrons to kwa hapo tu exist hapo.
Kwa hivyo
so
kumaanisha our world hata venye siona iko more complex kuliko hata venye tunaiona. Ukienda atomic level vitu zina they act differently and not even follow the normal physics laws. Is that right?
You can say like that. Okay, for example, I can say this. We have two worlds. We have an outside world and an inside world. The outside world is the one that we talk of creation. The creation, I can use the Big Bang theory.
Yes.
What banged and vibrated and started forming. It started in those microscopic particles, the electrons, the protons. They came together, they joined, whatever formed.
Okay.
Now the inside world is us, our brain, the neutrons inside us. They are somehow very small. 1 is to 10,000.
Yes.
Very
minute.
Yeah. So what happens there? It's so minute.
So it is the same thing. So it's like you have a universe in your brain.
Yeah, because those neutrons in our brain, they are so microscopic.
And they still use electricity and light.
Yes,
they communicate.
Yeah, that's how light comes to our eyes and it goes to our brain. And it does what? And we are able to see this object. Yeah.
Okay. The next theory is whole theory. Sasa hii whole theory ni zile ma black hole ama ni nini hizi? What is the whole theory?
Whole theory is one of, in fact, whole theory is the most beautiful equation in physics is that one of a whole theory. It was done by the one person, a scientist called Paul Dirac. Paul Dirac was trying to get now. Our basic thing now today is unity. We are bringing unity today.
Yes. So bringing things together.
So Paul Dirac was trying to bring an example of a whole theory because we have black holes in our universe. Yes. Yeah. Now he was trying to calculate this being that is so dense and this being that is so infinite. In physics, the word infinite is not, it's hatutumiangi sana jina infinite.
Si vitu mingi infinite.
So tunajaribu
lazima zikiwe calculated.
So tunajaribu nini sana. Kuhakikisha hatutumii jina infinite sana. So the absence of an electron of energy could be interpreted by an observer in the vacuum. Na bado huyo observer kwambie kuna particle hapo. Ndio maana nasema physics hatutakai kutumia jina infinite because obviously we should observe it.
Kuna observer na wewe observe infinity.
So he was trying to bring us to look for a position of a particle. Even if we say it is absent, we have to look for the position of that particle. You say it is not here. It's not there. It must be somewhere.
It has to be somewhere.
Yes. Like now the black holes, we cannot say it is in our planet because we all know that it is so dense. It can even swan
a whole solar system.
So before we say it is nowhere, we have to observe it is nowhere. It is not here or not there. We have to show where it is because it is in one place, in somewhere.
So basically, is it observed already? Have they observed a black hole?
There is M87. It exists between galaxies, but not in our galaxy. And the black holes are so massive that they are more than the weight of the sun, the star itself. Yeah.
Okay.
So the sun, if they are more massive than the sun, it is possible that in case they came to our orbit, they can even swallow our entire planet system.
Okay.
But they are observed in the galaxies. They are
Away, light years away.
Yeah.
Okay.
Okay.
Next thing tulikuwa tumeona ni holographic theory. Holographic theory ni nini?
Holographic theory the existence of a boundary in our universe. So Beck and Einstein, there is somebody called Jacob Beck and Einstein. He tried to look for we exist in a universe that we can see it has a boundary.
Yes.
So those boundaries are the ones that bring about the holographic theory. Yeah, he tried to tell us now at the end of our boundaries, at the curvatures, those particles, those electrons at the end of our universe, they somehow affect everything that happens in our hologram. Now, let us look at our universe as something like a hologram, something like you can enter inside.
Okay.
And you can go outside.
Okay.
So now the holographic theory that Beck and Einstein was trying to look at is the entropy. Entropy is a measure of order or disorder, is a measure of disorder.
Okay.
So the entropy of our universe is measured through the holographic theory itself. We try to look at the particles, how are they arranged? If they are they in order to say that they can form a human being like me.
So the atoms that are come together and arrange themselves to bring like a monkey or a human being or a rock whatever it is.
Yeah. And he tried to bring it and say like we have a certain order that we follow to have existed in our universe. And that is something that comes in our hologram. Our universe becomes something like a hologram.
So kwa hii holographic theory, nilikuwa okay, I was trying to understand it. Ni zile vitu tunaona kwa TV, sci-fi, wase wana teleport ati atoms zako ziko arranged in like what I've seen in those sci-fi ni kuna kitu kinaka kitube. So you go inside, then those atoms are rearranged into there's another tube in another location.
Yes.
So these atoms are sent in to the other tube.
Yes.
Is that kind of what holographic?
Yes, it's like that exactly. In fact, that's why I was telling you we have a boundary. We have a boundary somewhere. So now the atoms, let's call the atoms energy, and let's call the one you said you are transferred from here to that one information.
So, data.
Data. So here we have two things. We have energy, and that data we can call it volume. So now our energy or our atom in our case scenario here, we can say it's covering the surface area of our body. Now your question is, does our information exist?
Yes.
Now
that's our information. Yes.
I can say the surface area, the energy itself remains, but it remains inside. But the atoms, our information
has been taken to the other location.
So we remain only the surface area of that thing, but we don't have volume. We don't have anything. We don't have in that hologram. That one was done by the one physicist called Stephen Hawking.
Steve Hawking there.
Yeah, Steve Hawking was the one who was trying to differentiate. When you enter this hologram with all these boundaries, does our energy remain?
And does it go to the other location?
So he said, our energy remains, but our information does not remain. We don't have volume, we have surface area. Our energy remains in our hologram. Now we are talking about the holographic theory. how the conclusion. Our energy remains in our hologram, but the information goes
To the other location.
to the other location. And that information, we can call it volume. So energy, we can call it surface area. So our surface area remains, we don't have volume.
Okay. So, just thinking theoretically,
Yes.
teleportation
Yes.
can only work if you have the same number of atoms on the other side.
Yes.
If you have fewer atoms that are... Okay, now get to theoretically. First of all, do you believe teleportation is possible?
It is possible because we have quantum bits.
Okay.
Yeah.
We stop there.
We
Then,
have qubits, yeah.
so now,
Yes.
you're saying it is possible. You said teleportation is possible.
Yes.
So number two is, if teleportation is possible, can you teleport something to nothing? You have to have the same number of atoms.
Yes. That is how I was talking about information, because we are going to talk about our system, our quantum system now. Our computers work in binary digits. So let's imagine our computers, where that information goes. Let's imagine it goes to a black hole.
Yes.
In a way.
We don't know where it goes. It goes and disappears.
Does that, your question is, does that information remain in that black hole? That is the question. You are telling me you teleport.
Yes.
Is it going to be teleported to nothing?
Yes.
As a physicist, let's say that information is not going to remain.
It's not, the information is not going to the
And it's like deleting something.
But you have to have like the same number of atoms in the other chamber, because there are two chambers.
Yes.
There are two chambers.
In
right?
existence, yeah.
You have to have some atoms
Yeah.
in existence in the other chamber.
Yeah.
Because you can't teleport something to nothing, or nothing from nothing to something. Oh, okay.
That's how the information now there in our world. That's why we have quantum bits. Quantum
Qubits, yes.
Qubits. So qubits now will help us to navigate that problem.
Both states. So what you're saying, in short, is that teleportation will be possible once the quantum computers are working.
Yeah, and some countries like Japan, I think they are already using the qubits.
They are. Okay, some countries are using the quantum computing system already. Even big companies like Google, all of them are trying out this. It's only that they have not expanded in terms of practical use of such amount of power. Yeah. So then we can go to the next one, is time theory.
Time theory. Yeah. In our last episode, we were talking about time, and we had
Time as a constant. Time goes forward and can go back. It can go backward.
Yes. So physics define time as progression from past, present to the future.
Yeah.
And we had the funnel. You remember the funnel?
Yes, the funnel, yes.
The funnel was so linked by this, saying that we come from past, go to the future. We have several observations
that can prove this.
and we really tried to talk about them. The twin paradox.
Yes.
Two clocks, one is stationary and the other one is ticking. And we tried at least to discuss them.
Yes.
No, the time theory can be considered to be the fourth dimension. Our space, now when we were talking about string theory, we said there were Gabriel, the one who was trying to talk about the microscopic particles. We tried to look at our universe having more than 3 dimensions. So multi-dimensional.
Okay.
So now our time, before we talk anything, is the progression of any object or observable. Our time now will become the 4th dimension. Let's start our time being the 4th dimension in our universe. And that 4th dimension will somehow be affected by space.
Yeah.
Now the space-time.
Yes.
and that space-time will be affected by something else, like gravity.
Gravity. Yeah,
So-
there are other forces.
So that's our world now. You're going to turn from 3D to to 10D. Now we are heading
There's
to
so
20D.
many because there's so many things
Dimension.
that affect.
Yeah.
Anything can be affected by anything.
Yes.
That's what you mean.
Yeah. we are looking at our universe like there's XYZ. Now the one for height, depth,
Yes.
we are
We're
adding
adding
another
time.
dimension. Yeah, and that is time. So we can say there is the static theory of time, according to which time is like space, and there is no such thing as passage of time. And the second is the dynamic theory of time. When we say dynamic, is how time moves.
Moving. Okay.
And our time can also be in a dilation of
Can be a
dilate.
dilate.
Can we expand our time, or we can contract our time? The one we are talking about.
When you're moving, if you're moving,
Yes.
time goes slower.
Yeah.
That's what I understand.
Yes.
If you're static, time goes the same way.
Yes.
But if you're slower, time goes faster.
Good. So let's look on an example of an astronomer, and he left his twin brother on Earth. We were asking who will
Be older.
will be older. So if time is slower on Earth, the one on Earth will be
Older. Younger.
Yeah. Because now the one who is astronomer, they are astronaut, is still in motion.
He's in motion all the time and fast motion.
Yeah. But we have one thing that is affecting us, gravity. The one who is on Earth,
The gravity is higher.
9.8 meters per second.
Oh.
Physics still expects the one who our astronaut to be going against the gravity at the same gravity, 9.8 meters per second. But when he leaves space, now the space,
Yeah. It goes
everything
back.
changes.
It goes back to.
So we are going to see that person will change. One on Earth is going to experience faster time. So he's going to grow older.
Older, yeah.
And the one is space,
Because now of gravity now.
gravity now.
Wow. Okay.
Yeah, that's why we are going at. We are saying that we are going beyond the 3 dimensions. We are going to the 4th dimension. That is our time. Our time attracts space.
Yeah.
One dimension. Space attracts gravity. Another dimension.
So we live in a multidimensional universe.
Yeah, universe.
So then, what I read is, in this time theory is, time is an illusion and that reality is a network of events. This was so funny. At the time, the illusion,
That's
the reality, the network of events.
outside. We have static time theory and we have dynamic time theory. So this illusion is something like who came up with time? Yeah, time is an illusion because time is like space.
Yes.
And in our power episode, you said like if we were put in a cage,
Yes.
in a dark cage, and another person was seated somewhere and was looking at these shadows.
Yes. Yes.
The one who in the dark will not know anything.
Yeah,
That time is-
they'll not be able to know how much time has elapsed.
Yeah. But the one outside will know the shadow is changed.
So they can see the change in time.
Changing. Yeah.
Because of the light, the light, there's so many factors.
There are so many factors.
But when you're in the dark, there are no factors.
There are no factors.
You only have internal factors in your mind, in your brain, and they're not.
They are not what you be being like a person who is seeing what is happening in space in real world. That's why I'm saying like time and space, how they affect each other. And mathematically, we say speed is equals to distance over time.
Yes.
Well, this distance over this time in our universe is affected by two things. It's affected by the gravity, and it's affected by the curvature
The curvature of what?
of our universe.
Okay.
So if our universe is somehow curved, then now the statement you're saying about illusion,
Yes.
and we have gravity on our Earth,
Yes.
time is going to fly And that's where now the
In every position of the in space, time is varying. Uh-huh.
a very good example, because our topic is all about light.
Yes, yes.
When you are on Earth and you reflect your torch, you switch on, the beam of light travels straight.
Yes.
But on a space, the beam of light experiences a curvature.
Yes.
So
Because of the particles.
the particles. So if you now we said
Of the gravitational forces. Yes, of the forces.
the forces, now they are different.
Yeah.
Now here where I said speed is equals to distance over time. When we have a straight beam and another place we have a curved beam, we are going to measure this distance to a straight beam and this one of a curved beam, and you are going to see the distance of the beam, the one on Earth that is not curved, is going to be taller than the one that is curved.
Oh.
Yeah.
Okay.
The height.
The height.
Yeah. Let's say your torch is at this height on Earth.
Yeah.
But when it is curved, it will come
Go
like
down,
this.
go
Yeah.
down, yes.
So one is going to be shorter than the other.
Oh.
Yeah. So that really affects something of time.
Okay. Okay.
Yeah.
So this is what we were talking about last time, about time travel.
Curvature. That's
So after the okay, in short, what you are waiting for is the quantum computing that will make some of these theories actually be tested.
yeah, direct.
Actually be tested, yeah?
Yeah.
Because of the subatomic level of testing that needs to be done.
Observation. Yeah.
The observation that needs to be done.
Because as we said, Einstein, when he was dying, he had really many questions.
Yes.
Because there were no such observations, like the curvature and the straight beams.
Yes.
And for example, maybe Einstein had calculated the speed of something at 200,000 miles. But if it was quantum computed, it may be more or less like 186,000.
Oh, the actual figure.
The actual figure.
To be correct.
Yeah, to be correct.
What I understand with these quantum physics equations, the bigger the error, the farther you are from the truth.
That's no. So our father of physics may have differed with such observation, because obviously when you go outside to look for a theory, you expect to be the best. You don't expect to be challenged.
Yes.
So even himself, he was challenging his teachers. Then maybe his teachers also died before he died. They also died
With an unanswered question.
Yes. That is why our topic of relativity is so important in all these theories that we are talking about. Because Einstein really came with the topic of general relativity when it was affected by gravity.
And what exactly is relativity?
It's the relative nature of how we exist in our universe. And mostly how we exist, we are affected by a very strong factor, that is our gravity. But now quantum mechanics comes and tries to
go inside
this gravity, and it derives other things like space, time, curvatures.
Yeah.
So it does not go only for gravity.
Yeah.
But our Einstein was going only for gravity.
Okay. He was more focused on gravity and doing the test on gravity because that was the easiest at that time.
Yeah. Because like the Einstein equation of the speed of light is equals to mc squared. C squared is finite. Yeah, like you don't know c squared can be more than 300,000 kilometers per second. We just know it is that one.
It is that, so it is a constant.
It's a constant. Yeah, it is fixed. Speed, time, fixed. That's all.
Okay. So, scattering principle.
Scattering principle and superpositioning principle.
Superpositioning. Superposition.
Yeah.
What is superposition?
The superposition principle comes with our electrons, and we say our electron may be here, and may be here, and may be here. But when our electrons are entangled. There must be only two. And that's why I was talking about our neutrons in our brain cells. Our neutrons in our brain cells, they are entangled. And even a surgeon doing surgery, he knows how they are connected.
Yeah.
Like, a large network of neutrons, very small beings.
Yes.
But 10,000
Zimewekwa pamoja,
zimewekwa pamoja.
alafu zina move na speed of light.
Yeah. Now, when you cut this one, bro,
Yeah.
it
They affect all of this.
yeah, that network. Now, when you are superimposed, superpositioned, when this one is affected, it does not affect the other. And
So you're living in two different states.
yeah, and it's multi-state.
Okay.
Yeah.
So what are some of the applications of quantum superposition?
One application of quantum superposition is the quantum technology, such as quantum computers.
Quantum wao zenye zinaweza kuwa na two different states at the same time.
At the same time, existence. Yeah.
Okay.
Yeah, an example of an experiment that was performed in a superposition principle is the double slit experiment. Yeah, where light was observed to produce two beams in different slits. Yes.
Oh yes, in two slits, and then they did not go into the same location.
Yes.
They split.
They split.
They were quite wide.
Yes, the beam becomes very wide.
So with that experiment, the scattering experiment,
Yes.
I also thought about like it's all about quantum,
Yes.
the way the atom can live as a wave and as an atom. So now for me what I was thinking,
Yes.
when it hit the slit,
Yeah,
when it hit the slit, it became a wave. So that is why they were like,
they became more.
and in the middle they were less, and there were more. Actually, there were two lights. After going through the split,
Yeah,
there were many.
yeah, interface of pattern. Yeah,
Oh, that is an interface of pattern.
yeah, interference. And
Okay.
Yeah.
So when they were interfered with, they decided to go their own way. Ama change their state to away from an atom.
that's true. And
So now what I've realized is everything is quantum. Our body, our thinking,
Yes.
our everything.
our micro, everything micro. Yeah, even the one who explained about the universe forming a Big Bang theory
Yeah.
and everything coming out from it. And it's those atoms that joined together.
Oh.
And everything, the vibrations, the noise we hear, the light we see, are really connected atoms, very small particles, joining together, and they form something we can observe.
Hey, what is one of the things that is exciting you
Yeah.
in quantum physics? Okay. I'm a quantum realm. I want to take that.
Because we are in a digital world, then everybody should be going for technology. I think the best thing would be creating the strongest or the best firewall in the world.
Oh.
A firewall that could serve everybody very well.
Okay. So something that can protect everyone.
Like hackers, we exist in a world where we have really serious people, hackers.
Yeah.
Those hackers, they really fight those firewalls.
Yeah.
Like now, quantum computing, if it comes with the best firewalls in every game,
Yeah.
I think our world will be sorted.
So don't you think that once the quantum computer has come, even the hackers will have the same information, so they can break into your. So in quantum computing,
Yes.
the most things that the big companies and even the countries are afraid of is cyber security, because once you create a device that can compute in seconds things that can take years and years,
Yes.
and you find it fast, you see you'll be in an advantage and everyone else will be in a disadvantage. And that is why even like the China and the US, they all have independent laboratories trying to create, even big companies like have independent projects in research for quantum
Computers.
because once you know,
Yeah.
and you can break into anything. Because once that quantum computers come, you can break into every security that you ever thought about.
Direct.
Do 128-bit encryption, Those will be seconds, eh?
Right, you manipulate haraka sana. I was telling you, it's something like laser welding. The laser itself is laser.
Yes.
Yeah,
Light amplified.
Yeah, radiations.
Yeah.
Those two particles are so small.
But they can do so much damage
They can do so much.
once concentrated.
Yes. And people are using them. And also, they are using them both sides. They are
Good.
in
Yeah,
security.
but-
Yeah, that's true.
So at the end of then the other thing is, if you do quantum computing and then you add AI, then is that entropy?
Our world will finally come to another that I don't know how it will end.
Because
After that,
if-
other ends.
Like even now, like the computers that are there, even the quantum computers, they've been challenged to play chess with the best players and they beat them after a while. And those are controlled environment.
That's
Now think about AI plus quantum. So that will be a whole different.
Yes.
That will be a whole different
Scenario now.
scenario.
Yeah. Because now imagine our artificial intelligence currently it can even convert to your local language.
Yes, very fast.
Very fast.
Immediately actually.
So that computer and that artificial intelligence is the order we need now. I don't know whether our children will go to school.
By the way, so we have to. I think for the next topic, because we are about to end.
Yes.
For the next topic, we'll talk about the future of electronics, quantum physics. Because I think in the next 100 years or so, some of these experiments will be have done and proven, or even others that we don't even know about, and they will affect us both positively and negatively. So I think we can try and think about how the future will be.
Yeah, some also
In terms of,
we can also look at the future of our quantum. No, quantum. Even our most listeners who think it is something that you cannot understand.
Yeah.
So it means that they are going into all that they don't understand.
Yeah. Yeah, true.
So to our listeners, that which you don't understand is that which you understand.
Yes.
The quantum itself it's like that.
I remember I read a quote about quantum physics. That if you think you understand quantum physics, you don't understand. You have to be you have to be the other way around. When you don't understand, that's when you understand.
Yes. So to our listeners, that which you don't understand, you understand that one.
Yes.
That's true.
Asante sana. Now, for our listeners, mkitaka kuuliza maswali, if you are interested in the same topic, tuongeleshe hapo kwa comments, tusikie, tujue ni aje. And kama kawaida lazima tujibig up, tuko na radio station pale kwa mtandao. Hata hizi podcast ziko hapo unaweza sikiza, and some awesome music. To listen, you go to your browser, unaandika tu pale kwa URL bit.ly/nwks radio. The R is capital. Asante sana.